Okay. Uh, so this was same impeller actually we have tested, and you see this one volute casing, I said, right? This is volute casing. So this impeller will be going inside that one. Okay. Then your fluid will be exiting here and fluid will be entering through here. And if you see previous picture, the same thing actually, if you see this color, this area. Okay. So same thing it is here. Okay. So shaft you can see here. Okay. And impeller is here, yeah, at this location impeller. Okay. So impeller will be rotating at a very high speed, it will be delivering fluid here. Okay. So this one same. Fine. Radial, axial. Okay. Now I'll explain what is radial, what is axial. Head actually it is meter of water column, you can water column you can raise. Okay. So normally we do not say in terms of pressure, so we say how much water column height it can lift. So it will be easy to compare. Okay. Then radial flow, this is radial flow impeller. I said like actually going vertically up. Now what is mixed flow, what is axial flow? Let us say I have one shaft here, okay, and my impeller is here. Okay, fluid entering. So what is the angle? This is 90 degree. Okay, fluid entering, sorry, this one, fluid entering going up, so directly 90 degree. But in certain design fluid will be like this. Okay, so fluid will be entering and it will be going like this. So in this case actually it will be 45 degree. Okay, fluid entering and it is going like this. So it will be 45 degree. So it will not be so compact, rather it will be longer, and fluid will be entering and it will be going like this. Entering actually, this is axis, shaft axis means axis. Okay, actually entering, and it will not be going like this, it will be going like this. So this length will be longer. Okay, for especially ESP application, electric submersible pump, you need many stages. Many pumps will be connected in series. So in that case, if it is mixed flow, it will be very long. So in that case, this radial flow is better. It will make very compact system. Okay, and another is axial flow. Axial flow means like fan, ceiling fan, wind turbine. Fluid is entering like this and going like this. Okay, axial, mixed flow and radial flow. Okay, so when we are talking about radial flow, it will give higher head or higher pressure, or okay. Normally we say H, okay, and axial flow low head. I say like ceiling fan, if it is giving very high amount of head, actually you cannot work here, paper will be going here and there. Okay, so a small amount of air will be delivering, right, low head or low H. And radial flow, flow rate, how much fluid is it will be delivering per second, flow rate will be lower. Okay, and axial flow high flow rate. Okay, so wherever like wind turbine, very high amount of fluid it can deliver, but high pressure if you are giving, like say cyclone coming, wind turbine will not work, actually it will break. Okay, so very high amount of fluid if you give, low head, things will work, certain design. But for this case, very high flow rate I cannot give, but high head or let's say 10-story building I can deliver using this one. But using axial fan type impeller, if I design, it will not be able to deliver. Okay, but it can deliver very high volume flow rate. So now difference clear, axial flow, radial flow. So mixed flow will be in between two. Okay, so many cases people will be using mixed flow because it will be giving moderate flow rate, moderate head. So, if you want to compromise both, then mixed flow will be okay. But so you want to deliver fluid 134, 120, more than 120 floor like Burj Khalifa, or maybe 5,000 feet wellbore depth. So, one pump will not work. Okay. So, it will be having limitation one. Okay. So, then what they do? They will be putting in series 1, 2, 3, 4, 5, 6. Okay. So, how this look like? I have another model. This is actually actual ESP system, electric submersible pump system. So, multiple staging, how is centrifugal pump multiple staging will be done. So, this is radial flow. I have small impeller. This is also radial flow. Okay. It is having eye. This is shaft. There is shaft. This one shaft. Okay. And if see eye is here. Okay. Above, and impeller, inside impeller is the impeller exiting here. I don't know whether in camera it will be coming. Impeller exiting here. Okay. Then my casing is here. Okay. So, impeller eye, fluid is entering, and so this is my casing. But what is the diffuser? Diffuser is the white portion. White portion is diffuser. Okay. In white portion designed in such a way, like opposite of impeller, similar way. It will be taking high velocity fluid and reduce fluid velocity, increase fluid head, and impeller we put inside, and it become one stage, one rotor. This is called rotor, rotating, and stator or casing not rotating. This will be fixed on this one. If I put it here, so shaft can rotate my impeller. Okay, shaft can rotate, but this is not rotating my casing. Casing will be fixed on separate pipe. Okay, so that's why this is stator. Stator means casing part not rotating. Okay, casing part not rotating, only my impeller rotating. Shaft can rotate only impeller. Okay, that's why called rotor. Okay, again you see this design such a way, and this shaft design such a way, you put it, so there will be no relative motion. So, if I rotate it, impeller will be rotating. Okay. So, this is called rotor, and casing or volute casing, this part stator, not rotating. Okay. This is fixed on something, hold it, and this is rotate. So, when rotating, it will give high velocity fluid, this will be reducing fluid velocity. So, together become one stage. Okay. Together become one stage. So, this will be giving maybe 2 meter, 3 meter head. I did not calculate, but maybe like this. But you need 5,000 feet, right? 5,000 feet fluid when you have to deliver using ESP system, electric submersible pump. Electric submersible pump actually centrifugal pump. Centrifugal pump. This is centrifugal pump. This can be used as a electric submersible pump. Okay. So 100 to 100 stages will be there. So one stage, I have how many stages? 1, 2, 3, 4, 5, 6, 7. 7 stages ESP. Okay. I have 7 stages ESP. So fluid will be entering here and exiting here. Okay. And motor will be connected here. Motor will be rotating continuously. So when it is connected, the outside this black portion will not rotate. Inside that impeller will be rotating. Okay. And one impeller, one stator or rotor, and this impeller rotor also. Impeller or rotor. Impeller or rotor. Okay. It will be rotating. Stator not rotating. So all the impellers will be rotating together. Stator not rotating, and you are delivering fluid. So how much total head it will be giving? Let's say one stage delivering 1 meter. So 6 stages I have. So 6 meter total. So if I have 100 stages, 100 meter head I can develop. So simple calculation, fine. You can remember, like one stage developing 10 meter. So 100 stage, 10 into 100. Simple solution, right? Okay. Now surface production operation, why I am talking about ESP? In surface production operation also, in many cases you need higher flow rate and you need higher head also. So in that case you can create multiple stages of ESP, centrifugal pump. In that case I will not say ESP, this is not submerged, it will be on the surface. So in that case I can create rotor, casing, another rotor casing. So 1 stage, 2 stage, 3 stage, 4, 5 stages I can make very high amount of head. Okay, many surface production operation cases, for example hydraulic jet pump and other, you need very high pressure fluid to pump. So, in that case a reciprocating pump you can use, or in some cases you can use centrifugal pump multiple staging. Okay. So, multiple staging you are creating, purpose is that to increase total amount of head. One is given 10 meter, so 5 means 5 into 10, 50, simple solution. Okay. So, I in my laboratory I did only one stage calculation, one stage experiment. I did not check many stages. I had planned to use this multiple staging, but I did not do this one, but I purchased this one for class demonstration, so that the student can understand easily. And normally this ESP system, in actual ESP, this is non-metal. Actual metallic also, that will be like 1 or 2 inch thickness maximum. So, they can create a very long ESP system, but very large number of ESP also, I mean stages. This is called stage. One rotor, one stator called stage 1. Okay. Okay, I said like centrifugal pump will have higher flow rate, positive discharge pump lower flow rate. So, how does it look like? Just wait. Okay. So, centrifugal pump will have, the basic thing is that to know the difference, you have to draw Q and H curve, flow rate and head. So, flow rate, this is flow rate, okay, and this is head. Normally meter of water column, and flow rate normally, like if you are using SI unit, then meter, then flow rate will be meter cube per second or meter cube per minute or bar per hour. Then the curve will be normally looking like this. Okay, this horizontally it will start, and finally it will be coming to 0 almost. Okay, and efficiency curve, this is HQ. Okay, and efficiency will be like this. At certain point efficiency will be maximum, then this is eta. So, I can put eta also next same axis, efficiency. Okay, so centrifugal pump, this is for centrifugal. Okay, so for centrifugal pump will have efficiency maximum, this is called best efficiency point. Okay, so best efficiency point or BEP. So, best efficiency point means you are getting very high amount of head and using low amount of energy. Okay, and your target should be to run pump at BEP, but exactly BEP running is difficult. So, normally the company say, okay, you run within certain range, okay, maybe plus minus 20% maximum within that range. This is called range of operation, operating range. Okay, if you are running within this operating range, the cavitation probability will be lower, your system efficiency will be much higher, and system will be running smoothly. But if you are violating this norm, then maybe cavitation will be coming, or maybe some other issue will be coming. Okay, so whenever you are running a pump, you should maintain this one. Okay, now another curve will be coming, system curve, almost straight line. Okay, system curve means how much power it is consuming, or brake power. Here one term is called brake power, hydraulic efficiency, brake horsepower. Have you heard the term? Brake horsepower is like this, like pump shaft is there, okay, the shaft. Now, I am applying brake to resist it. So, how much energy will be required to resist the brake? Okay, that they call brake horsepower. So, the term you will be hearing many times, brake horsepower, because you are just using brake, you are reducing the speed, you are making 0. Okay, so how much force you are applying? So, using that, if you calculate, then that will be giving brake horsepower. Okay, that will be more than your hydraulic horsepower. Hydraulic horsepower means your pump is delivering a certain fluid. So, I have some formula for hydraulic horsepower like rho QH. Okay, this is your formula for total amount of energy. Okay, so pump will have certain efficiency. So, how much energy it is taking actually for delivering certain amount of fluid. So, this much of energy it is taking, but if I calculate brake horsepower, it will brake horsepower will be more energy. Okay, but if I want to calculate electrical energy, it will be much more. So, you are giving, let us say 100 kilowatt electrical energy. So, after motor losses, it may be 90 kilowatt remaining. Then after other losses, maybe 80 kilowatt remaining. then finally pump will be delivering maybe 70 kilowatt. Okay, so everywhere there will be losses. So 100 you are giving, maybe you are giving 70 getting. Okay, so that's why overall efficiency when you are calculating, then you have to calculate electrical to how much you are getting. How much you are getting means rho QH by eta. Rho means density of fluid, eta means efficiency of the pump. This is theoretical power. Okay, efficiency and density and flow rate, then head. Okay, so this is for centrifugal pump. So centrifugal basically 3 curves will be there. One will be HQ curve, flow rate and head, and another will be efficiency curve, another will be system curve or brake power curve. And some cases they have written brake power, but normally we say system curve. Okay, and if you like VFD, if you have, so VFD what will do, VFD if you change the speed, actually my HQ curve will be changing like this. So QH, so if you are increasing speed, head and Q will be increasing. Okay, when you are increasing speed, actually your energy consumption also will be increasing. Okay, so every pump will have their optimal speed range. So company will be providing this one. This is called pump characteristic curves. Okay, so you see the title I have given, characteristic curve. So pump characteristic curve will be given by company, because company will be testing pump and they will be drawing the curves. Many curves will be there actually similar. Okay, parallel curve, this curve, this, that curve. So you have, and the company will say, okay, you run your pump within that range, then things will be okay. If you are violating the norm, then things will be wrong. Now positive displacement pump. Positive displacement pump, normally curve will be like this, HQ. Okay, especially HQ curve we show to difference. Why HQ curve? Because in positive displacement pump, does not matter whatever flow rate is there, whatever head is there, flow rate will be same. Okay, say you take certain reciprocating pump and you keep speed same. Okay, so when you are keeping speed same, it can raise infinity head, infinity pressure. Any 100 floor, 200 floor, 1000 floor water lifting, once reciprocating pump can work, but centrifugal pump cannot work, because you can see HQ curve in centrifugal pump, it is like this. Okay, so centrifugal pump is having limitation. Okay, is the maximum head limitation per stage, but reciprocating pump there is no limitation. So any amount of fluid you can deliver. This is one difference. One difference is that flow rate and head. Centrifugal pump can develop limited amount of head. Okay, this is this picture, limited head. All right, but reciprocating pump there is no head limitation. We Q vertical line, that is not touching to H. So any amount of pressure will be possible, infinity possible actually, but there practically infinity not possible, because there will be certain leakage and other thing. I will explain later how the leakage is occurring. But ideally it will be infinity. But centrifugal pump, ideally practically it will not be infinity, it will be having certain range. But you see the Q, amount of Q, centrifugal pump will be higher. Q means flow rate will be higher. Okay, so that's why many cases the users will be deciding which one to use for their application. Okay, for example, you want a very high flow rate, but head not very important. For example, some water logging is there in a road, nearby road. So reciprocating pump using the does not make any sense. You will be using one centrifugal pump and quickly you remove the water, right? Because high volume water is there. So just you have to remove. All right. Many cases like building basement, water will be filled, and you have to remove the water as soon as possible. So head not matter in that case. You need flow rate high. So you will be buying or hiring one centrifugal pump. Okay, but you are like say new buildings are there in IIT, you want to lift fluid, so centrifugal pump one stage may not be working. So you have to use multiple stage or use reciprocating. Okay, so I said like characteristic curves, HQ curves are there, but how to draw it? Let's try. Okay, let's say this experiment I want to do in laboratory. Okay, so what we'll do, initially open all the valves. Okay, You see all there is no restriction, switch on the pump, okay, and pump will be running normally 1400 rpm. Actually in my laboratory it was 1400 rpm pump, okay. If I change pump speed, my flow rate and other things will be changing. So initially you start with 1400 rpm, what the existing company said, and piping, whatever any valves, anything is there, completely open. Now start switch on the pump. What will happen? It will give maximum flow rate. This is centrifugal pump, okay. So it will be giving maximum QH. It will be giving maximum flow rate here. So that time my pressure gauge, where is my pressure gauge? Flow valve. So maybe somewhere pressure gauge will be here, okay. Oh, pressure gauge is here, I think. This one pressure gauge, okay. So pressure gauge will be showing very low pressure because there is no restriction of fluid, okay. So I will be getting is right side, I have put one dot, you see this curve. Now after few seconds or few minutes, you just turn this flow control valve. You see one flow control valve is there. Try to close the valve little bit. So you are closing means flow will be little bit lower and pressure will be increasing in the pressure gauge. Pressure gauge will be showing little bit changing, okay. So that time flow will be little bit reduced, pressure will be increasing little bit, okay. Then again little bit close, 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 okay, you will get it. So I asked the student not to close completely, because if you are closing suddenly pressure will be shooting up and system can fail. So just try to close up to certain level, then just draw a curve and join the curve to y axis. So this way I get HQ curve, okay. So if I see HQ data, if I take like H may be like initially 0, okay, needle is not moving, and flow rate may be 4 meter cube or 4, okay. So some value, I am not writing unit. Then H2 3, 2.5, 2, 3, 1, okay, 3, head is not changing, maybe 0.5, okay. So that way I can draw the curve, okay. But if I have PCP, I tested PCP also, progressive cavity pump, I told, okay. So this PCP will be giving different story. How? Instead of centrifugal pump, same place I put PCP, okay. So in that case what will happen? I will be changing H, this is centrifugal, this is PCP or positive displacement pump, okay. So in that case I will draw separate another one, QH, okay. Initially everything open, my flow rate will be very high, H will be very low. Now you close a little bit, keeping RPM same. So it will be delivering same amount of fluid, okay. So my same amount of fluid, but pressure it will be showing higher, that pressure gauge. Again close further, flow rate will not change, flow rate will not change, flow rate will not change, okay. Like your heart, if you have any blockage, heart will try to pump, okay, but so same amount of pressure it will try to generate, but you are restricting. So what will happen? You will have pain or some heart extra pulsation or something will be coming, right. So that is also positive displacement type. So it will be giving same amount of flow rate, same flow rate, okay, irrespective of pressure, okay. So curve is vertical, fine. Now in centrifugal pump, in VFD, if I can measure my power, how much I am giving. In VFD, variable frequency driven electrical input part, right? VFD is electrical input. Okay. So if I know the power, how much giving, power electrical, and then how much hydraulic head pressure we are developing, like say theoretical power required for pump to deliver certain amount, rho QH by eta. Eta means pump efficiency, okay. So and if you know motor efficiency, eta motor, eta pump. So overall efficiency will be like eta pump into eta motor, okay. So from here actually you can calculate how much you are giving input, how much you are getting, how much losses is there. Fine. Whenever you are talking about pump, so pump will have some specific speed. From there also, actually you can differentiate between different pumps, okay, among different pumps. So specific speed formula is it N S equals N root over Q H power 3 by 4, okay, this formula. N is your rotational speed of shaft, okay. I have shaft rotation speed N, normally it will be RPM, Q is flow rate, H is differential head at B, best efficiency point. I already told best efficiency point, right? BP. N is specific speed. So from this specific speed, actually you can check whether my pump will be coming under centrifugal category, axial category, radial, or maybe positive displacement category. Okay. So if I see this one, this is radial tall blade radial, and this is axial. So axial flow means like this, and this tall blade means fluid will be moving like this. This short blade also like this. This is mixed flow, more 45 degree. Okay. So specific speed will be low here. High here. Okay. Low specific speed, high specific speed, and my reciprocating pump will be coming here. Reciprocating or positive displacement type will be coming the tall blade, nearby tall blade. Okay. If you are using RPM, let's say this is RPM, GPM, this is meter, then this value will be coming like this is 500, this is about 1000, this is 15,000. Okay. So this is unit dependent. So it is not universal. So if I give value in, let's say, barrel and meter, so this value will be changing. Okay. So you should not remember exactly the values for all the unit universal, because its unit is having, so it will not be universal. Okay. Based on unit you have to check specific speed. Fine. So low specific speed means high head, okay, head high, flow rate low. High specific speed means flow rate high, head low. Fine. So you should remember. So low specific speed pump, reciprocating type, tall radial blade pump, and high specific speed axial flow pump or axial flow machines, maybe turbine also possible. So their flow rate is very high, but head is very low. Okay. So in exam I can give question like this, if two pump, if different values I give, I can ask you, which range it will be. It will be low specific range or high specific range, or you have to select a pump for certain application. Okay. So then you can quickly calculate, you can check. Fine. NPSH, when you are talking about in centrifugal pump, it will have two components. One will be NPSH A, and will be NPSH R. NPSH net positive suction head. Suction head. Okay. Whenever you are using any pump, centrifugal especially, so you must know centrifugal pump NPSH. So company will be providing the data, and company is saying like NPSH A is 5 meter, then you have to keep more NPSH R 5 meter, then NPSH A must be more than 5 meter. So NPSH A, this must be maintained. R means required, company will give. And NPSH A means available, you must maintain. Okay, if you are a production engineer, so you have to check how much NPSH is available for you. If you are not maintaining, what will happen? There will be cavitation. Vapor formation will be there, so vapor will be creating cavitation in your system, so system will fail. So you must maintain the NPSH when you are running any pump. Okay, for a positive displacement pump also certain amount of pressure is required, but for centrifugal pump it is very much serious. Cavitation will be more important. in centrifugal pump. Okay. The formula NPSH A equals P1 by rho g minus PV by rho g plus Vs square by 2g. Okay. So, P1 absolute pressure of the inlet of the, at inlet of the pump, absolute pressure at inlet. Okay. And PV is vapor pressure at inlet. What happened when pump is sucking fluid, okay, from suction pipe, if suction pipe pressure becomes very low, so bubble formation will be there. Okay. So, you have seen this at if create lower pressure, so bubble will be formed. So, you should not create so much low pressure, so that bubble will form. Okay. So, this vapor pressure also will check. Vapor pressure depends on temperature. Okay. Your say initially company said like you maintain 5 meter NPSH R and you think everything okay, but fluid temperature increased. If fluid temperature increase, vapor pressure will go down. When vapor pressure will go down, automatically vapor maybe will be creating. Okay. So, that also you have to check. So, vapor pressure also very important for your NPSH calculation. So, NPSH will be calculated in the suction side, not delivery side. Okay. When fluid is sucked by pump, okay. I have pump here, right. So, this side pressure will be checked, okay, not delivery side. Vs square, V square means friction, velocity of the fluid, Okay, some more parameters will be coming here. This is simplest form. Another parameter will be coming for friction. If friction is very high, again you are giving more resistance, means some pressure drop will be there. Again cavitation probability will be increasing. If you have some pipe bend, lots of pipe bend, again there will be problem. If you have sharp bend, you have some notch or something, so everything will be giving pressure drop, friction high. So that will be also hampering your NPSH. Okay, NPSH A. R you are not controlling, R given by company, A you have to maintain. So when you are check NPSH available or not, you have to check fluid temperature, fluid property. Instead of water you are using let's say petrol, so your vapor pressure changed, the boiling point changed, means it will not work, right. Then your pipe diameter you have to check, you have any sharp bend, if you have long pipe you have, so all the parameters you have to check, which will give you pressure drop or vapor pressure change. Okay. If you are not checking, your NPSH will be having problem. Okay. That will be giving your cavitation. So NPSH equals HP, some other formula, detailed formula is there, H vapor HST minus HF minus HA. Okay. So detailed things are there, whatever I was talking about, HST will be plus. Okay. So absolute head surface of the liquid tank. Okay. So let's say, okay, so how much pressure is here. Okay. Then HF is friction head. Okay. Because of fluid friction, some pressure will be dropped, certain amount pressure already there because of atmospheric pressure, but that will be minus friction, and HA will be acceleration head with fluid pipe diameter very low, then again pressure drop will be high. Okay. So pressure drop is very high, then acceleration head. Okay. And HVP H vapor pressure, Okay. So vapor pressure is depending on temperature, fine. H static head. Okay. The static head means like if you have, this is plus, if your water level height is more than your pump is here, water level height is here, so that will be static head, so that will be added actually, but it is below the pump, then it will be minus. Okay. So the static head above the pump center line, above center line. Okay. Now cavitation. So cavitation actually if you are not maintaining NPSH, what will happen? It will be sucking fluid and vapor will be created or bubbles will be created. Bubble is created when it is going towards exit, bubble will be again collapsing. So, vapor creation and collapsing is called cavitation. So, because of collapsing actually the metal particle will get removed slowly from the metal surface and it will be giving noise, vibration and metal particle getting removed. So, because of that one your pump life will be longer or instantaneous fill may be possible or pump slowly it will be getting eroded. So, that will be having negative impact. So, one term is called cavitation number. So, cavitation number or cavitation parameter number or cavitation parameter. Okay, P minus PV rho V square by 2. So, pressure minus vapor pressure divided by inertial pressure. Okay. So, sigma less than 0 cavitation will occur. Okay. So, you should remember NPSH is important part when you are running a pump and it will have cavitation. So, cavitation parameter also you should remember and this basic formula you should remember, okay, especially NPSH A, NPSH R, those terms full form where cavitation can occur, impeller inlet fluid sucking, then when pressure is developing, so that certain area cavitation will be occurring. Okay, thank you very much for today's lecture. We will start next topic the next day.